If you've had a go at sketching some of these curves, then hopefully you've recognized for x squared minus x to the 4 we can factorize, and you should be able to recognize that you'll get roots at 0 and at -1 and at 1. X squared minus x to the 4 is the same as x times 1 minus x times 1 plus x. Also, it's a repeated root at 0, and the symmetry that we can suspect is going on, we can see really is true because all of the powers of x are even. This is an even function, it's going to have symmetry about the y-axis. So because it's a negative quartic, we know it starts low and ends low. It'll come up through -1. It'll have a stationary point at 0 because it's a repeated root, and it'll go back down through 1. If you differentiate and look for more stationary points, you'll identify exactly what we would expect. There is another stationary point somewhere between -1 and 0, a maximum, and then another maximum between 0 and 1. This is what your curve should look like. The next one, we can get a rough idea, but we need to start by thinking about this curve to get there. For a start, we can rule out anything where x is below -1 or above 1, because then x squared minus x to the 4 will be negative and we can't square root it. In between those points, think carefully about what happens when you square a number between 0 and 1. If you square something between 0 and 1, you get a smaller result. 0.5 squared is 0.25, for instance. Well, that means the opposite happens if you square root. If you square root a quarter, you'll get a half. So that's going to pull this point up, and in fact it will pull all the points up except where the value is actually 0. So at 0, the square root of 0 is 0, but anywhere else it's going to be quite a bit higher. 0.1, for instance, if you square it, you get 0.01. So if you square root 0.01, you get 0.1, which is 10 times higher. The effect is magnified when you're close to the origin. So we're going to get some interesting behavior around here. Not sure if your graph fully appreciated exactly how extreme that is, but this is the result we get. When we're close to 1, the rate at which the graph comes up is very steep here. And as we get to here, there is a sudden change. This is called a cusp. This sudden change in the gradient is due to the fact that here we're getting exactly the same result as over here. For small negative values of x and small positive values of x, we have exactly the same y value, and when we square root, we get larger y values. Well, that's just the positive square root. So if we're interested in sketching y squared equals x squared minus x to the 4, we're also going to need to consider the negative square root. That's not so difficult once we've got the positive one, because it's going to be the exact negative of what we've already got. But it's worth noticing now that this curve we've ended up with looks like a complete loop. If we just draw the single curve, and GeoGebra can do this, this is called an implicit function because x and y are not given directly in terms of each other. We don't have y equals something involving x, or even x equals something involving y. We've got some combination of x's and y's that are connected. In this case, it's a pretty straightforward one. It's still a function of y on one side and a function of x on the other, but it's not just y equals, it's y squared equals. And yet we get this interesting pattern. It looks like a closed loop, this infinity sign. And it might be worth investigating why that happens, because it looks like a bit of a fluke. It's to do with the structure that's hiding behind this combination of squares and powers of 4. What I want to do next is show you a point that can move smoothly around this curve, and it follows a fairly standard parametrization. This is what parametric equations is all about. We're trying to find a way to map onto, in this case, a two-dimensional plane, something with a third parameter determining the motion. Something which otherwise would be quite complicated. This is a weird sort of curve to construct. This one happens to have a relatively nice representation involving x and y, but often the representations are either horrible, completely unhelpful, or impossible to construct properly. But this point A is following a fairly nice process. Capital A, is the point which is determined by cos of a number for the x-coordinate and a half of sine of 2 times that same number. And that number can be whatever we like. And I've set this to be a slider that varies between 0 and 2 pi.